Hey everybody, this is your pre-lab for part two of our dissolved oxygen module for the Green River project. Last week, you focused on standardizing the thiosulfate solution so that we could have a precise concentration of your solution in order to now titrate the Green River samples and find the dissolved oxygen levels. Note that the Green River samples this week have already been treated with the divalent manganese in order to fix the oxygen. That was done when the samples were first taken. They've also been treated, though, with solution one containing the 3 molar sodium iodide and the 8 molar sodium hydroxide, as well as the concentrated sulfuric acid, so that you don't have to do any of that solution preparation like you did for part one, standardizing your solution. When you get your 30 milliliters of the Green River sample spot, you'll find that they're already that sort of yellowish brown color. So you'll literally need to just get your 30 milliliter sample and start titrating away. Remember that what you'll do is add some of the thiosulfate until you get a bit more of a pale yellow color. At that point, you can add your starch, which will turn the solution that blue, black, inky sort of color. Then start titrating very, very carefully until all of that blue color does disappear and you have a clear solution. That is the visual indicator of the end point of our reaction. Your goal for each of the Green River sample spots and the 4 ppm standard, which we'll talk about at the end, is to have three titrations that are all very, very close to each other. I'm not necessarily going to set a parameter on that closeness. Some of it will depend because some of these titrations will take more thiosulfate than others. But you want three that are, again, pretty close to each other. And feel free to check with your instructor to see how they feel about how close your measurements are. And so let's talk about what we're actually going to do with that information then. So ultimately, for each of the Green River sample spots and for your 4 ppm standard, you are then going to have three titration volumes. Again, for each individual spot, you'll have three titration volumes. You then be able to simply average those. And so for each Green River sample spot and the 4 ppm standard, you will ultimately have an average titration volume. And so let's think about what that really means. And so you're going to be able to know the moles of this S2O3. And we'll see that calculation in just a second. But remember, what you're finding is the volume of S2O3 that you use, because this is the actual reaction that you are running in the burette. You've got your S2O3 in the burette, and ultimately all of the steps that have already been done for you lead up to this I2 solution down in your Green River sample spot. It's that I2 which makes it the yellowish, the sort of that brownish yellowish color that it is. And so the starch indicator that we're using turns blue in the presence of I2. So as long as there is still iodine in there, elemental iodine in there, the solution will be blue. And so when it turns clear, we know that we've added exactly enough of the S2O3 to react with all of the I2 in there. You'll know the volume, that's your average titrated volume. We also know the molarity. That was the whole point of what we did last week. If you know the volume and the molarity, you can know the number of moles. If you know the number of moles of S2O3 that were added, then we can use our stoichiometric ratio here, two S2O3s for every one I2, to know how much I2 was present down in your sample solution. That I2 had to have come here from equation 3. That I2 from equation 3 had to have come from our manganese sulfate. That manganese sulfate was generated here in reaction 2, came from this manganese oxohydroxide, which ultimately was created in equation 1 from the dissolved oxygen. So all we have to do, as long as we know the moles of S2O3 that were used, which again are simply found by using our titrated volume and our standardized concentration, we can know the moles of S2O3 that were used and ultimately use our stoichiometric ratios to backtrack and find out how many moles of O2 were actually present. Let's take a look at that and then see what we'll do with that information. And so here's here's the calculation that you are going to run through. This X here is going to be your average titration. And so for each Green River sample spot, you're going to run through this calculation. And so this X is that average of your 3 titrations. Again, for each Green River sample spot. And so this will be your average titrated amount. We're then going to multiply that by the standardized molarity that you found last week. That should be both written on your bottles and down in your lab notebook. So you should have that concentration written down. And so that'll be the concentration you found last week. Again, let's just take a peek at what that is. When we multiply those, what we're going to know is how many moles of S2O3 we had to have used to react with the iodine. We're then simply going to use our stoichiometric ratios, 2 S2O3s for every 1 I2, 1 I2 to 1 manganese sulfate, 1 manganese sulfate to 1 manganese oxohydroxide, 2 manganese oxohydroxide to every 1 O2. So we'll be able to use those ratios in order to get to the moles of O2 initially present. And that's what we see here. And so take a look and convince yourself that that's how the units are working out. You can see it here. Liters of S2O3 cancels out. Moles of S2O3 cancels out. Moles of I2 cancels out. Moles of manganese sulfate cancels out. Moles of manganese oxohydroxide cancels out. Ultimately left with moles of O2. Pretty simple calculation. Your average titrated volume in liters, remember that you are going to be measuring from your burette in milliliters, so you will have to convert that over to liters. But that average titrated volume in liters multiplied by your molarity, divide by 2, get to the moles of O2. So if we think about what that really is, remember you've got your 30 milliliters of your Green River sample solution down in your beaker or flask. Within that 30 milliliters, we now know how many moles of O2 were initially present there. Remember what we're shooting for here. We're shooting for the concentration of O2. We know the number of moles. We know how many liters were in that initial sample, that 30 milliliters. So you've got your 30 milliliter Green River sample solution. We know the number of moles now. We're just going to divide those. So however many moles you found in your previous calculation, divide that by 0.030 liters. That's just the 30 milliliters converted over to liters. That's going to tell you what the molarity of the O2 was in the Green River sample spot. So we're almost there. Our goal was to find the concentration of O2, but typically when we're talking about any sort of environmental concentrations, we usually work with parts per million. So we're going to convert that to ppm. ppm is equivalent to milligrams per liter. And so we've already got molarity, moles per liter. And so you're going to take the molarity from the previous calculation. And really, all we need to do then is convert this moles over to milligrams. That's a simple enough calculation that we've done 1,000 times at this point. So we're going to use our molar mass to convert to grams of O2, grams to milligrams, gets us to ppm O2. And that's it. Let's look through an example, though. And so this is completely fictional data that I made up just for the purposes of this presentation. And so let's say, for example, that I had an average titrated volume of one of the Green River sample spots. Let's say I had an average titrated volume of 12.5 milliliters. I'm going to convert that over to liters, first of all. So I get 0.0125 liters. And then I'm going to use the standardized molarity. Remember, this is the standardized molarity of your solution. Most of those are in the ballpark of 0.0035, sort of in that range. But you're going to use your actual number there. This is just a fictional example. But then we send it through the rest of our process to get to the moles of O2. So 0.0125 times 0.00350 divided by 2 divided by 2 gets us to 1.09 times 10 to the negative fifth moles of O2. So in this fictional example, that would be how many moles of O2 were in our 30 milliliter beaker, our 30 milliliter sample. So we're then going to take that moles of O2, divide it by 0.03 liters, and we find that we have 3.65 times 10 to the negative fourth molar O2. We're now going to take that number and convert it to ppm. Multiply it by 31.998 times 1,000 gets us to 11.7 ppm O2 in this example. Plenty of dissolved oxygen in there for the fish population to thrive. Remember that when we're looking at the level of O2, anything that's really above sort of an 8 to 10 level, anything up in that range or above, plenty of oxygen for fish populations to live and to thrive and be very happy. When we start getting below 8, sort of a 6 to 8 sort of range, then we start getting into a range that individual fish are probably going to be okay, but the population itself really isn't going to thrive. There's just not quite enough oxygen there. We start getting below a 5 range, we're below 6. Now we're getting to where individual fish are going to start to suffer. Much below 4 or 5 ppm, and we start getting a lot of fish kill and fish dying off. So this particular fictional example, 11.7, more than enough dissolved oxygen there. And so that's ultimately what we're looking for the Green River samples is what is that dissolved oxygen level, and is it enough for the population to thrive? Or are we starting to look maybe at some of these sample spots that possibly things start to suffer a little bit? Or of particular interest might be the spot where we actually saw the fish kill down there at Site C. Well, what's the dissolved oxygen looking like there? Is that what is contributing to the fish dying off? That's what we're looking for. Now, most of the time for our Green River project in general, you have no way to judge your accuracy because you don't know what the actual real numbers are supposed to be. In a process like this, though, we do have a way to start to look at our accuracy, not because you know what the Green River sample spots are. We do, and we're going to take a look at accuracy based on that. But what we can do here with something like this is we can take a 4 ppm standard. So something that we know is definitely 4 ppm. We've created it. We made up the sample itself. We know that it is 4 ppm O2. You can titrate that. See how close you get to 4 ppm. That is what's going to allow us to judge the accuracy of our results for part 2 here of our determination of dissolved oxygen. Basically, how close are you to 4 ppm when you titrate the 4 ppm standard? And so we'll be able to make some judgments on the accuracy of our data as well. As far as precision, we'll evaluate that using percent RSD as we have been for the entire semester so far. You'll look at your titration volumes in general, see how close they are, and evaluate your precision that way. But there it is. There is task 2 of our dissolved oxygen lab, ultimately looking to find the dissolved oxygen at each of the Green River sample spots to see if there is enough oxygen there for the fish to live and to thrive. And so when you come in, at least in my sections, other instructors may tell you different or want you to do something different. But in my sections, feel free to just come in and start titrating away and use this pre-lab video to help walk you through the final analysis. And so I hope this was helpful, and I'll just leave you with happy titrating because you are going to be doing a bunch of it. Have a great day.